Hi, welcome to today's lesson on basic architectural acoustics. Today we are going to cover wavelength, frequency, how wavelength and frequency are related, the speed of sound in air, the pitch, tone, loudness, a unit called Phons, which is used to talk about subjective hearing of humans, and then we are going to talk about the range of human hearing, that is from the threshold of audibility to the threshold of pain. So let us begin. Okay, so the first thing we're going to talk about is sound, noise and music. Noise and music, although they're both sounds, there's a difference between noise and music. Let's find out what the difference is. Noise is basically an unwanted sound, or a sound that is annoying or disturbing, or something that makes you uncomfortable or is interfering with your communication with somebody else. Music, on the other hand, is something that you enjoy, that you think is pleasurable, that you think soothes your mind. But always remember, one man's music is another man's noise. One person may think something is music to them, but it could be noise to their neighbor. So please keep that in mind. So before I talk about wavelength, I'd like to show you this animation by Professor Dan Russell of Penn State University. If you can see the dots in red, they are particles that are highlighted. You can see how they move to and fro from a center mean point, and it is due to this to and fro motion that we get waves. You can see the direction of travel of the wave. It is from left to right. But the particles move to and fro about a mean position. The places where molecules are less is known as rarefaction, and the places where molecules are more is known as compression. So the distance between two compressions, or the distance between two rarefactions, is known as the wavelength. Frequency is basically how many of these to and fro motions, complete to and fro motion cycles, are completed within 1 second. That is frequency. Now I'm going to show you another animation. This is propagation of sound in 2 dimensions. The previous slide you saw of the propagation of waves in only 1 dimension, that is from left to right. Here you can see the propagation of sound in 2 dimensions. Just observe the motion of the particles. It's to and fro motion of the particles. So this is how sound travels in 2 dimensions. Okay, so sound is a wave. Sound is a wave both in space and in time. Usually when we are talking about variation of sound pressure, we are talking about the variation in atmospheric pressure. There is certain atmospheric pressure everywhere on Earth. At sea level, that atmospheric pressure is approximately 101 kilopascals. The variation in this atmospheric pressure is known as the sound pressure. The sound pressure is the sound pressure variation is very small compared to the actual atmospheric pressure. Sound has both a frequency and a wavelength. Frequency is a time dependent characteristic of sound, whereas wavelength is a space dependent characteristic of sound. In sound, frequency and wavelength are interrelated. They are not independent of each other. Okay, so what is frequency? Frequency is a time dependent characteristic of sound. Frequency is basically the number of complete to and fro cycles that happen per second, like I showed you in the animation before. I mean the time taken between two for one compression to happen and another compression to arrive at the same point is known as a time period. A shorter time period means higher frequency. A longer time period means lower frequency. Wavelength is a space dependent characteristic of sound. Wavelength is measured in the units of distance. Basically a short wavelength means a higher frequency, and a large wavelength means a lower frequency. So wavelength is the distance between two compressions or rarefactions. It's a distance between the centers of two compressions or rarefactions in a medium where a sound wave is traveling. So wavelength and frequency, they are not independent of each other, they are related by the speed of sound. Here you can see the formulae that lambda is wavelength, f is frequency, c is the speed of sound. The wavelength and frequency are inversely proportional to each other, and they're related to each other using the constant that is the speed of sound. Now let us see what the speed of sound is at sea level at 20 degrees Celsius. So the speed of sound in air at 20 degrees Celsius is 343 meters per second approximately. That is quite fast, but not as fast as light. It's very minuscule compared to the speed of light. So when we talk about sound measurement, we're usually talking about sound pressure. Sound pressure can be measured in two ways, either by measuring the pressure or by measuring the particle velocity. Sound intensity is measured in watts per meter square, that is the amount of energy per second passing through a unit area. Sound power is measured in watts, that is joules per second, that is the amount of energy emitted by a source per unit time. So these are the three parameters in which sound measurement can be made. Sound intensity is derived from sound pressure, and sound power is derived from sound intensity. So at the end of the day, the basic measurement that needs to be done is a sound pressure level measurement, and from that you can derive all the other parameters. So let's talk about decibels. Why do we use decibels? Why don't we use just pascals or watts or watts per meter square to describe sound pressure, sound power, and sound intensity? Well, the problem with that is human hearing is not linear to the increase in sound pressure. So therefore we use decibels. First the Bell unit was used, but however it was found that the decibel unit closely met the needs of scientists, so the decibel scale is used today. Decibels are a logarithmic ratio, therefore they do not have any units, they are just a unitless number. Okay, so there are three types of decibels. One is the sound pressure level. Whenever we use the term level in front of sound pressure, it means that the unit is in decibels. We have to abbreviate it as a dBSPL to make sure that we are talking about the sound pressure level, not the other ones. So when we talk about sound intensity level, we say dBSIL. That means that is decibels of the sound intensity level. And so similarly for sound power level is dBSWL. That means it is the decibels of the sound power level. So dBSWL is the sound power level. Well, I'm not going to give you the formulae for the decibels because it's not really necessary to understand that in this basic course. Okay, so there are three decibel levels that is a sound pressure level, sound intensity level, and sound power level. They have different uses. The sound power level is basically used to make measurements of background noise in room acoustics, in environmental noise, in community noise, and industrial noise. The sound intensity level is mainly used to make sound intensity measurements so that you can calculate the sound power level of any noise generating equipment. The sound power level is just a decibel level to measure the amount of energy radiated by noise source per unit time. It's a measure of that, but it is in decibels. Okay, so one thing you need to know about adding decibels is you cannot add them like simple arithmetic. You cannot say 40 dB plus 40 dB is 80 dB. Usually for two incoherent sources, that is two sources that are producing completely uncorrelated sound, if you add if they are both playing at 40 decibels, then if you add the decibels of both, you will get around 43 dB. That is a 3 dB increase. If there are two equal sources which are incoherent, then the addition of the two results in a 3 dB increase in the sound pressure level. So just remember 40 dB plus 40 dB is not 80 dB. So now let us talk about sound transmission in a free field. By free field I mean free space. There are no surfaces that the sound encounters. By free space I don't mean empty space. This space does contain a fluid, let's say air. So in this scenario, suppose a omnidirectional point source is emitting sound, then the sound travels in all 3 dimensions equally in all directions. This is how a point source works. So the sound pressure level decreases by 6 dB per doubling of distance from the sound source. This is also summarized in the inverse square law for intensity. Inverse square law for intensity states that there's going to be a 6 dB reduction in sound pressure level or sound intensity level if you double the distance from the sound source. So here you can look at a distance r from the sound source, the sound power level is 90 decibels. At distance 2r from the sound source, the decibel level is 84 dB, the sound pressure level is 84 dB. So sound intensity is inversely proportional to the square of the distance from the point source. The point source needs to be omnidirectional for this to be true. Sound pressure level decreases by 6 decibels per doubling of distance, be it in sound intensity level or be it in sound pressure level. So let's talk about what we call psychoacoustics, or the the acoustics of how people hear. The basics of psychoacoustics is that we need to know what range of frequencies a young healthy human can hear. The hearing range for humans is between 20 Hz and 20,000 Hz for young healthy individuals. Hearing range usually shortens as we are exposed to high levels of noise or other forms of hearing loss, and it also the hearing range also decreases with age. Hearing loss mainly affects our ability to hear the high frequencies, and there may be an explanation for that. So this is the anatomy of the human ear. You can see the outer ear, that is the pinna, and the air hits the pinna and enters the ear canal, and as it enters the ear canal it vibrates the eardrum. Once the eardrum is vibrated, the vibration is passed on to the 3 smallest bones in the human body. They are called the malleus, incus and stapes. The malleus is also called the hammer. The hammer. The incus is called the anvil, and the stapes is called the stirrup. I hope I'm right on this. If I've made a mistake, please do correct me. And these bones act as a mechanical amplifier. They take the vibrations from the eardrum and amplify them and pass them on to the oval window, which is where the bones meet the cochlea. The cochlea is the detection system and it is in the inner ear. The cochlea is filled with fluid and it contains hair cells. The hair cells detect the various frequencies and the amplitude of sound, and they turn it into nervous signals, which are then interpreted by your brain as sound. One important thing to keep in mind is the outer ear and the middle ear are filled with air, whereas the inner ear, the cochlea, is filled with fluid. There's one more interesting fact here. You can see 3 semicircular canals on top of the cochlea. These semicircular canals are mainly there for the balance. So they tell you whether you're upside down, whether you're sleeping, whether you're inclined at an angle, and so on. So this is a very interesting fact. You might want to keep that in mind. The anatomy of the human ear is very important because ultimately we're designing our spaces for human beings. So this is the unwinded cochlea, so to say. At the base, that's where the oval window is. That is where the bone meets the cochlea. The vibrations are then passed on to the fluid in the cochlea. The hair cells in the cochlea detect the various frequencies and the amplitudes of the various frequencies, and they turn them into nerve signals to go to the brain, where you perceive it as a sound. Now let's talk about the hearing range for humans. The hearing range in terms of frequency is from 20 Hz to 20 kilohertz for a young healthy human person. But there is also 2 other things: the threshold of hearing and the threshold of pain. The threshold of hearing is the amount of sound pressure that needs to exist for you to just about hear that sound. At 1 kilohertz, this is usually defined as 2 into 10 to the power of minus 5 pascals, and at the threshold of pain is a particular sound pressure level where you start to feel pain in your ears. You feel very uncomfortable, and you really start to feel the pain. You could also feel some sort of ringing in your ears, or you might not be able to hear at all when you reach the threshold of pain. So these two are the threshold of hearing and threshold of pain. While the threshold of hearing can be as low as 2 into 10 to the power of minus 5 pascals, the threshold of pain can be the sound pressure at the threshold of pain can be several pascals. Let's talk about pitch. Pitch is related to the frequency content of a sound signal. If it's a complex sound signal, then the pitch is related to the lowest component in that sound signal. So if the lowest frequency of a sound signal is low, then we call it as low pitch. If the lowest frequency component of a complex signal is high, then we call it high pitch. So I hope you know the difference between high pitch and low pitch. Usually people refer to people's voices as low pitched voice or a high pitched voice. Sounds that are shrill are known as high pitch, and sounds that are less shrill are known as low pitch. Let me play some audio files just so you get an understanding of how low frequency sounds and how high frequency sounds, so you get an idea of how different pitch sounds. Okay, so now I'm going to play a 100 hertz sound wave. Just please listen to it. So now I'm going to play a 100 hertz sound signal, so please listen to it. Now I'm going to play a 200 hertz sound wave. This is a 200 hertz sound wave. So this is a 1000 hertz or a 1 kilohertz sound wave. So which one did you think was low pitched and which one did you think was high pitched? Answer in the comments below. So one more thing I would urge you to do is to listen to these 3 noise signals in fixed volume. Just make sure the volume is low enough that the loudest noise is not too loud for you, that it makes you uncomfortable. So you may notice that the low frequency sounds sound much less louder than the 1 kilohertz sound. There's a reason for this, and we'll explain that in the coming time. So now we're going to talk about tone. There can be 2 types of tones, a pure tone and a complex tone. A pure tone is a pure sinusoidal signal of any frequency. It is just one, it has only one frequency component, whereas a complex tone contains many different frequencies in its content. And a complex tone, an example for that is the human voice or music or most things that we hear. Pure tones are pure sinusoidal signals. They're produced on computers, or they're produced by very special instruments. The audio samples that you listen to, that is the 200 hertz tone, the 100 hertz tone, and the 1 kilohertz tone, these are pure tones. Just keep that in mind. My voice is an example of a complex tone. So loudness is the subjective perception of sound. It's how loud we think something is. That's what we call as loudness. Phons are an attempt by scientists to put a number to loudness. Although loudness differs, the perception of loudness differs from person to person. Scientists have done studies on a large group of people and tried to put numbers to loudness. That is where the unit Phon comes in. There's also a unit called zones, but we're not going to discuss that here. So let's look at Phons. So Phons are a subjective unit based on psychoacoustic studies. on large groups of humans to determine the equal loudness at various frequencies. Suppose you hear a wave at 1 kilohertz. How loud should a tone at say 100 hertz be for it to be heard similarly loud as it was at 1 kilohertz. That is why the Phons were invented. And let's see the equal loudness contours. So these are the equal loudness contours. You can see the lines for 10 Phon, 20 Phon, 30 Phon, 40 Phon, etc. So whichever noise spectrum closely matches with the curve, that curve will be taken as the Phon level of that particular sound. So these are what are called the equal loudness contours. With that, I'm going to end here. In the next class, we're going to talk about reflections and room acoustics. Thank you for listening. I hope you enjoyed this video. For more videos, please like, share, comment, and subscribe. I look forward to seeing you in the next video. Thank you.